Hello, I am Ajitha, Assistant Professor EC Department, Tech Multitech, Dr.Rangarajan, Dr.Sakunthala Engineering College. Dear students, today we are going to solve a problem in Smith chart. A transmission line has a characteristic impedance of 300 ohm and terminated in a load ZL is equal to 150 plus J150 ohm. Find the following using Smith chart. First one, VSWR. Second, reflection coefficient. Third, input impedance at a distance 0.1 lambda from load. Fourth one, position of first voltage minimum and maximum from load. So, first step is to write down the given data. What is given? Given Z0 is equal to 300 ohm and ZL is equal to 150 plus J 150 ohm. In order to draw the Smith chart, first step is to follow is to find the normalized load impedance. The impedance given in the question must be divided with the characteristic impedance in order to get the normalized load impedance. So ZL dash, that is the normalized load impedance, is equal to ZL by Z0, that is equal to 150 plus J 150 divided by 300, which will give you 0.5 plus J 0.5 ohm. So we must take the first value as the resistance value and the second one as the reactance value. Resistance R is equal to 0.5 and the reactance X is also equal to 0.5. So to plot the normalized load impedance on Smith chart at P and draw the impedance circle from R is equal to 0. Okay. Next, VSWR can be directly calculated from the intersection of impedance circle at X equal to 0 line on the right hand side of the Smith chart. So this is the Smith chart. The circles are the resistance circle. These circles are the resistance circle and these circles are the reactance circle. So first step is to plot the point load impedance. Okay, what is the value of load impedance? 0.5 plus J 0.5 ohm. Okay, so this is the center point 1.0. This is the center point, mark it as O. Okay, this is the center point, mark it as O. Next, we want to plot the resistance circle. Resistance value is, these circles are the resistance value. So 0.5. This circle 0.5. 0.5. Next, the reactance value is also 0.5. Okay. Okay. These two values will meet at a point. That point is the load impedance value ZL dash. Okay. Mark it as P. Okay. Next, we must take this OP as radius. Take this OP as radius and draw a circle. The circle is called the VSWR circle. Okay, the circle is VSWR circle. Okay, next, this circle will intersect at a point in the right hand side, that is this R is equal to 0 line. So mark that point and that point will give the VSWR value. Okay, that point will give you the VSWR value. What is the value? So this is the point 2.0, 2.2, 2.4, 2.5. So I got as 2.5. So we have got this VSWR point as 2.5. Okay, from the Smith chart. Next step is to draw a straight line OP to P dash. Okay, first draw a straight line OP to P dash. OP joining O and P, draw a straight line towards outside. Okay, towards outside and mark that point. Here we will get the load value, the wavelength of load, the wavelength towards generator, mark that as 0.08, 0.08246, 0.0246. So this value is 0.086 lambda. Okay, this is the load value, position of load, 0.086 lambda. Okay, next one is to calculate the reflection coefficient. So you must draw the same radius, here downside, and draw an arc that will cut at the point here. So the top side, the top line, you will get the reflection coefficient. It is given here, reflection coefficient 0, 0.10, 0.20, 0.30, 0.40, 402, 4023. So I have got the reflection coefficient value, that is modulus of K, magnitude of reflection coefficient as 0.43. Okay. Next, we want to calculate this reflection coefficient. We have calculated as 0.43. We have to calculate the phase angle. How to calculate that? Just look here. The angle of the reflection coefficient, it is given as the angle of the reflection coefficient in the graph. Just look here. Here it is given as 120 degree. Okay, 120, here 110 degree. Next, 112, 114, 116, 118, nearly 118 or 117 degree. So I have got this angle phi is equal to 117 degree. Okay, so what's the value? I have got this phase angle as 117 degree. Okay, the phase angle phi is equal to 117 degree. So the reflection angle value is 0.43 at an angle 117 degree. Okay. The third one is to calculate the input impedance at a distance 0.1 lambda from the load. For that, we want to, this is the location of the load. We want the input impedance at a distance of 0.1 lambda from the load. So the location of the load is at 0.086 lambda. Just we want to add that 0.1 lambda. So what is the value? 0.186 lambda. Okay, 0.186 lambda. So just take a note at 0.186 lambda. Where is it located? 0.18, 0.182, 184, 186. Okay, this is the point. Just mark that point as 0.186 lambda and draw a straight line towards the center. Okay, draw a straight line towards the center. Okay, that point, that line will intersect at the point in the circle. That point will give you the input impedance, normalized input impedance ZS dash. So first take the resistance circle, next take the reactance circle. What is the resistance circle value? Value is here, this is the value, this is the circle. What is the value? 1.4. This is the value. Okay, this is the value 1.4. Similarly, the reactance circle is, this is the value 1.0, 1.1. So input impedance we have got at 1.4 plus 1.1 J. Okay, plus 1.1 J. This is the value for normalized input impedance. Next, the fourth one is to calculate the position of first voltage minimum and maximum from the load. For that, just mark this point. The right hand side of the graph is V max. Okay, voltage maximum, and the left hand side as V minimum. So this is the location of the load. The right hand side is the location of voltage maximum. This is the voltage maximum and this is the voltage minimum. First, we want to calculate the position of voltage maximum from the load, that is this point. Okay, this much, the distance between these 2 points. Just take in the clockwise direction alone. Take the values only in the clockwise direction. We want to calculate the position of voltage maximum from this load and the position of voltage minimum from this load in the clockwise direction. So, in order to calculate the position of voltage maximum, first take the circles. First, the half semicircle, the upper half semicircle, the value of upper half semicircle is 0.25 lambda. Similarly, the value of the lower half semicircle is also is equal to 0.25 lambda. The whole circle will give you the 0.5 lambda. So, when we subtract this value, the distance of this value from 0.25 lambda, we will get this point, right? The position of voltage maximum from the load. The whole value 0.25 lambda minus this value will give you the position of voltage maximum from the load. So, how to calculate that? Position of voltage maximum is equal to 0.25 lambda minus 0.086 lambda. 0.25 lambda minus 0.086 lambda will give you the value of 0.164 lambda. Okay. So, the position of voltage maximum from the load value is equal to 0.164 lambda. Similarly, for position of voltage minimum from the load, just we want to add this value to this semicircle value. Semicircle value is 0.25 lambda plus this value is 0.16 value. Now, just now we have calculated. So, the B mean position is equal to 0.164 lambda plus 0.25 lambda will give you the value of 0.414 lambda. Okay. So, this is about Smith chart. First, a small recap. First step to draw the Smith chart is to calculate the normalized impedance. Normalized load impedance can be calculated by dividing the load impedance with the characteristic impedance Z0, right? First, just plot that value here. Then take this center point and the load impedance value as the radius and draw the circle. That circle is called the VSWR circle. The VSWR circle will intersect in the right hand side with the R is equal to 0 line. That point is called VSWR, that is voltage standing wave ratio. That will give you the voltage standing wave ratio as 2.5. Next, extend this OP line towards the outer circle, towards outside. That point will give you the location of the load. Next, we want to calculate the input impedance. In order to calculate the input impedance from the load, just add 0.1 lambda plus this location of the load will give you the 0.186 lambda, and just plot that point in the outer circle. Extend that point towards the center. That line and the VSWR circle will intersect at a point, and that point will give you the input impedance value. Okay. In order to calculate the reflection value, reflection coefficient value, take this OP as the radius, draw a arc in the first line, that is reflection coefficient line, and that will give the magnitude of the reflection coefficient as 0.43. In order to calculate the phase angle, just look here, angle of the reflection coefficient will give you the phase angle phi is equal to 117 degree. Next, last one is to calculate the position of voltage maximum and position of voltage minimum. For that, consider this upper half semicircle is 0.25 lambda and the lower half semicircle is 0.25 lambda. First, we want to calculate the values only in the clockwise direction. First, for calculating this position of voltage maximum, take this 0.25 lambda and minus 0.25 lambda minus this value 0.086 lambda. So, this will give you the position of the voltage maximum. In order to calculate the position of voltage minimum from the load, take this value, add this value to this 0.25 lambda will give you the position of voltage minimum. Okay friends, I hope you have understood well. Thank you.